Hello there, Mr. Sutton here, bringing you the Algebra 2 8.5 lesson on the probability of disjoint and overlapping events. And as the title suggests, that's what we're going to be finding, those probabilities. Let's get to it. Open this one up, we're going to pose a question to you. Let's say that you and a friend are playing a card game in which you will each draw one card from separate decks. In order to win, you need a red card or a club, while your friend needs a black card or a spade. Do you have the same chance of winning? Why not? Pause the video and give it some thought, and then we'll come back to it. Alright, so it turns out you do not have the same chance of winning. Let's go into why that is. So there's two different situations here. This first situation where we needed a red card or a club, well, red cards and clubs are two completely different categories. We would call these disjoint or mutually exclusive events, events that have no outcomes in common. There are no red cards that are also clubs. So in this case, to find your probability, you would just have to add the individual probabilities of the events together. You get all the red cards and you also get all the clubs in your corner there. So as a formula, we can say that P of A or B, notice the or here, would just be P of A plus P of B. Now the other situation where your friend needed a black card or a spade, well, the problem there is that there are some spades that, well, actually there's some black cards that are spades. All spades are black cards and some black cards are spades. Half of them actually. So this is an example of what we would call overlapping events. These are events that have some outcomes in common. Specifically here we have all the spades are part of both groups. So in this situation, we can't just add the two probabilities together. In this situation, if I were to add the black cards and the spades together, I would be double counting the spades, both as spades and as black cards. So in a situation like this, we not only have to add the probabilities, but we also have to subtract the overlapping portion. So as a formula for overlapping events, we would say that P of A or B equals P of A plus P of B. We still have to add the probabilities of the two groups, but now we have to subtract P of A and B, the overlap. Now that we've gotten a little bit of background on disjoint and overlapping probability, pause the video and see if you can figure out this one, where we're randomly selecting a card and we want the probability that we have a 10 or a face card. Alright, let's see how this one worked out. So first, it's a good idea to figure out what type of probability you're dealing with. Since there are no 10s that are also face cards or vice versa, these are disjoint events. There's no overlap between them. So we can use just our regular add the probabilities format. Specifically, P of A plus P of B. Let me just clearly identify what A and B are in this situation. A is drawing a 10. Well, B is drawing a face card. So we just need to find these two probabilities and add them. The probability of drawing a 10, well, there's 4 10s in a deck of 52, so 4 out of 52. And we're not going to reduce this yet because, as we can see up here, we're going to be adding fractions together. So we're actually going to reduce after we add the fractions together. If we reduce too early, then we'll have to get a common denominator, and that just takes longer. Now for the probability of B, of getting a face card, there's 12 face cards for each of the Jack, Queen, and King. So we have 12 out of 52 there. So the probability of getting 10 or a face card is just going to be 4 out of 52 plus 12 over 52, which is 16 over 52. And now we can reduce that. That'll be 4/13. Here's another one for us to try out. Pause the video and see if you can find the probability that the card that we select is a face card or a spade. Alright, so taking a look at our two groups, there are some face cards that are spades. I mean, here's one example, the Queen of Spades, kind of staring right at us. So this is going to be an overlapping situation, and we're going to have to do P of A plus P of B minus P of A and B. So we have to subtract that overlap. In this case, A is a face card, and B refers to a spade. The probability of a face card, we saw that on the last example. That's going to be 12 out of 52 still. Now for spades, remember that there's 13 of each suit in a deck, so 13 out of 52. And again, we're not going to reduce those just yet. Let's go ahead now and figure out P of A and B, because we also need that for this formula. So we're asking how many spades are also face cards, or vice versa. Well, there's 3 spades that are face cards. Here's one of them, the Queen of Spades. We also have the Jack and the King of Spades. So 3 out of 52. So putting all this together, we've got 12 out of 52 plus 13 out of 52 minus those 3 overlapping cards out of 52. So this is going to be 25 minus 3, which is 22 out of 52. And now we can reduce that to, let me just reduce by 2's here, that'll be 11 over 26. On this next problem, we have an archaeology lab receiving 150 artifacts for processing. And of these, they're telling us 108 are made of clay or have coloring. 81 artifacts are made of clay. 34 have coloring. We want the probability that a randomly picked artifact has both, made of clay and has coloring. Okay, well, we've got 2 different events here. One of those is being made of clay. The other event is having coloring. And is this an overlapping or disjoint situation? There's an or involved, so we want to kind of bring that language into it. Well, since we're asking literally for an artifact that has overlap between these 2 events, yes, I would say this is probably an overlapping situation. So we've got our overlapping formula. P of A or B equals P of A plus P of B minus P of A and B. But here's the problem. We're not looking for the probability of the or here. They actually already gave us that. We're looking for the probability of P of A and B. So how are we going to get that? Well, we have a formula. The nice thing about formulas is that they can be rearranged, and you can, in fact, rearrange this formula, the overlapping formula, to solve for the overlap itself. So that would be a big hint to getting you started on this one. Pause the video and see if you can run with that and take it the rest of the way. Alright, so if I want to get P of A and B by itself on one side of the equal sign, I have to add it to the left side and then immediately subtract the P of A or B over to the right side. So I'm effectively switching the and the or when I do that. Add it over here and subtract this over here. So now I see that I need to figure out P of A, P of B, and P of A or B in order to figure out the and. So P of A, that's the probability it's made of clay. Well, they said that there were 81 artifacts made of clay, and that was out of a total of 150. So P of A would be 81 over 150. The coloring, that would be the 34 that they told us had coloring out of the 150. And for the or, we're asking how many have clay or coloring, and they actually told us that in the beginning. That was 108. So 108 over 150. So let's just put it all together. We've got 81 over 150 plus 34 over 150 minus 108 over 150. 81 plus 34 is going to be, let me think, 125? Is that right? No, actually, 115. 115. And then 115 minus 108 is going to be 7. So 7 over 150 would be our answer on this one. If you're taking the CP non-honors version of the course, this is the end of the lesson for you. You can turn off the video and try out some disjoint overlapping probability sorts of problems. If you're doing the honors, we've got one more problem for you, so stay tuned. For this problem on the honor set, we have the American Diabetes Association estimating that 9.4% of people in the US have diabetes, and then they're saying a medical lab developed a simple test that is 98% accurate for people who have diabetes and 95% accurate for people who do not have it, which is kind of interesting that there's a different percentage for each of those. So it sounds like that we have fewer false negatives than false positives. Anyway, we want, if we give the test to a randomly selected person, we want the probability that our diagnosis is correct. So this is a little bit tricky because we've got 2 groups of people. We've got the people who have the disease, who have one measure of accuracy, and the people who don't have the disease, who have another level of accuracy. So we need a way to combine those. Let's start by naming our events. So there's 2 events going on here. First off, we have the possibility that someone has diabetes or does not. So 2 outcomes for that. The other thing going on is whether or not they have diabetes, there's the question of whether the test gives them the correct diagnosis. So we have to kind of mix these two things together. So you can see here, just based on these different percentages, that event B is going to depend on event A. If we have diabetes, then we have to do something for B. If we don't, then we have to do something different. And we've got multiple sorts of things going on. Because if you're asking for the probability of a correct diagnosis, you're asking for the probability that the people who have diabetes get the right diagnosis, but also the probability that the people who don't have it get the right diagnosis. When you have multiple rules and dependencies going on, a tree diagram can often be helpful. So we're going to build one of those together, and then we'll let you off at some juncture to see if you can take it the rest of the way and complete this study. So let's talk about event A first off, because event B depends on event A. So event A, there's 2 outcomes, that we have diabetes or do not. So let's let P of A represent having diabetes, and they said that there's a 9.4% chance, so that would be 0.094 if we express that as a decimal. And now let's also talk about not having diabetes. That's the complement of A. It's just going to be 1 minus the percent chance that you had diabetes. So 1 minus 0.094. Well, let's get out the calculator just to be on the safe side. So we've got 1 minus 0.094. That's going to be 0.906. Now, for each of these possibilities, we've got 2 branch-offs. One of them where we have the correct diagnosis, and then the complement of that, the incorrect diagnosis. So let's talk about the diabetics first. So one branch-off is we've got a correct diagnosis. They said if you have the disease, there's a 98% chance that you'll get the right diagnosis. So we can say P of B given A would be 0.98. And then P of not B, not getting the correct diagnosis, given that you have the disease, that would be 1 minus this, so 0.002. And then let's do the same thing for the folks who don't have the disease. So correct diagnosis, they said, was 95%. So P of B given not A would be 0.95. And then this is going to be weird. P of not B given not A, so not getting the correct diagnosis given that you don't have the disease, that would be the leftover of 0.05. So here are all our conditional probabilities and the original event A probabilities. Pause the video at this point and see if you can use this information in a way that will tell us the probability overall that we have the correct diagnosis. And again, you need to take into account both the people who have the disease and the people who don't. All right, so what we're really aiming at here is we're trying to find a combined probability. This is actually going to be a big OR statement. We want the probability of A and B, so has the disease and gets the correct diagnosis, or we also want the probability of not A and B, doesn't have the disease and gets the correct diagnosis. So these are both conditional probabilities. These are both dependent probabilities, dependent events. So for P of A and B, that's going to be 0.094 times the conditional probability of B given A, so 0.98. And then since we have an OR going on in here, we have to add. We're going to be adding 0.906 times correct diagnosis for that, 0.95. And now the calculator is going to have to take it from here. So 0.094 times 0.98 plus 0.906 times 0.95. And that's a grand total of 0.953 if we round it off. So there's a 95.3% chance that this test will give us the correct diagnosis regardless of whether we have the disease or not. So that's it for this one. You might say this is where I leave you. Until next time, Mr. Sutton signing off.